Okay, so our next speaker, come on. All right, great. Our next speaker is Anton Lorenzen from the University of Edinburgh, and he'll be talking about property-based testing, but not as we might be familiar with it. Instead, it's about amortized time complexity. So take it away, Anton.
Yeah, thank you, Liam. I have probably one of the longest paper titles at this conference. And it basically chains together a bunch of concepts. So lightweight testing, you can already see, I'll use QuickCheck later in my talk. Amortized time complexity, in particular the persistent one that Okasaki studied. And then I'll present something new, which I call the credit monad. But to start with, I want to start with the amortized time complexity. And I want to explain why that's a concept that matters. So let's look at probably the simplest queue you can imagine in Haskell, and you've probably written a program like this. So if you want to have a queue in Haskell, you take two lists, a front list and a back list. You push by putting something onto the back list, and you pop from the queue by taking something from the front. And you can already see that that probably doesn't work very long, because if you only push to the back and you only take from the front, at some point the front will be empty. And so you'll add this extra function called queue that checks that whenever your front list is empty, you'll reverse the back list and install that as the new front list. And so that is a very simple and functional implementation of having a queue. But it does have a bit of a problem, namely that the worst case runtime of this is not so good. So of course pushing is very quick, you just add a constructor there. But then popping can be quite expensive, because you might have to reverse the entire back list. And so the question is this actually a good queue implementation after all? And so if we think about this worst case, we might think actually not, right? Any individual pop operation might take a long time. And now we might worry, what if we do a bunch of like n push operations and m pop operations? What is the runtime of all of this? And you might worry that it's n times m, which would of course be very bad. But you can kind of convince yourself that it's actually not so bad, because every element is put onto the real list and will be reversed at some point onto the front, and that can only happen once. So if you kind of look at this in a combined manner, like n push and n pop operations, well, you have to pay for n push operations, and you have to pay for n reversals, potentially, and then for m pops, which is, of course, a much better runtime than the n times m you might have imagined naively, right? And so in an amortized sense, we might say pop takes O of one time. And so the way you can make this argument precise is by reasoning about credits. So let's say we look at this example. So we have a queue. So we push 1, 2, 3, 4 into the empty queue, and then we take one element out. So we start with the empty queue, and we push one element in, and we immediately have to reverse it onto the front. And then we push one element into the backlist. And so here we have to do no work for the reversal, but I'll kind of pretend that we do, and I'll accumulate this credit, which I've marked by this coin there. And so I keep pushing until I have 3 elements in the real list, and then I have 3 credits accumulated. And now, once I actually do the pop, well, I can kind of say that the pop is free, because, of course, I have to do this big reversal, but instead of kind of paying for it at this point, I just say I convert the credits I have into like a time, like a clock, into like an execution step. And so by this way, I can see that actually I don't have to pay anything more than what I've paid for before already. And so this works really well in the sequential execution, which is also how this technique was first studied. In basically an imperative language, everything would be fine. But of course, we are in a functional language. And so in a functional language, everything is not fine, because we can actually pop from the same queue twice. And so if we do this last pop twice, well, the first time it's all fine. We just convert all of the credits into the times, and everything's good. But now, if we pop again, we have to do the exact same reversal again, right? Because the pop operations work on the same queue. There's no work being shared. So actually, I do end up doing a lot more work, and so the second pop actually does cost time linear in the length of the list. And so this is the fundamental problem that motivated Chris Okasaki's work on purely functional data structures, which is that if you work in a persistent setting, every element can transit from the real list to the front list many times. And so if you do n push operations and then you do m pop operations on the exact same version of the list, you actually can get n times m time complexity for this, right? And so we should have some data structures that can work better in a persistent setting. Okay, and so Chris Okasaki also found the solution to how to do this. And the basic idea is to use thunks, because thunks have a really nice property, namely that they're only evaluated once. So this is not completely true in a multi-threaded setting, perhaps, but at least in a single-threaded setting, we can kind of say, well, if you put some expression into a thunk and you'll force it at some point, the first time you force it, you actually have to do all of the work, but then all the forces afterwards just memorize the result of the first time, so you don't have to spend more work. And like this is even true in a persistent setting, so even if there's a bunch of references to your thunks, the work only gets done once. And so if we wanted to make this example work, assuming we had like some magic way of putting our reversal operation into a thunk, well then the first time we force it, we actually spend all of the credits, and we arrive at the result and everything's fine. And then the second time we pop, well, we now look at the same thunk, we get the memoized result, and we don't have to do any extra work. So if we can somehow change our data structure so that this is possible, we can have the time complexity that we want, even in a persistent setting. And so what I've been doing in my work is kind of trying to take this reasoning and turn it into a DSL that you can use in Haskell, to kind of check this kind of reasoning for yourself. And that is something that I call the credit monad. And it has several features. So the first, of course, you need some notion of cost. So you can't really inspect Haskell and ask, like, how long does this expression take? But you have to specify it yourself. So I have this tick constructor that just consumes one time step. Then I have a class called monad lazy. And the idea behind this is that we need to, that of course Haskell is a lazy language, but if you, oh, that's not good. Did I do that? Okay, good. So of course Haskell is a lazy language, but if we're writing a DSL, we actually need to model laziness ourselves, because we have to kind of reason about the laziness kind of from the outside, so we can't use the implicit laziness that's already there. And the way you do this is by having a delay constructor. So delay takes a monadic computation and puts it into a thunk without looking at it. You can also actually just put a value in, so this kind of an already memoized thunk. And then you have a forcing function which takes a thunk and gives you the result of the computation. And the idea is that in the implementation, force, of course, memoizes the result and only runs a thunk once. And then to actually reason about the credits, we'll now combine all of this into the credit monad. And the credit monad has two functions. One is called credit width. So if I'm given a thunk and I'm given some credits, which is a number, I can put those credits onto the thunk. And I also have a function called has at least, which kind of asserts that a thunk has at least a certain amount of credits and fails otherwise. So let's look at one actual example for how you would use this. And for this, I'll use the implicit queue that Okasaki does. And I have to warn you, it's a bit more complicated than the simple queue I showed at first. But yeah, I think it's one of the simpler examples, maybe. So the way the implicit queue works is first that there's a data type called digit, which is either 0, 1, or 2 elements. And then the queue itself is either empty or it is a deep queue, which means you have 2 digits so that's kind of the front and your real list from the example. And then you have like this middle thing, which is a thunk for another implicit queue. And let's look at an example. So at the topmost, I say I have a deep node with a 1 and a 0 as my digits. And then in the middle, I have a thunk, which will be a push operation. which contains another deep node. And so here, one interesting thing is that the implicit queue that you have in the thunk stores pairs of the initial elements. So in the topmost deep node, I have a 1 in the 1 constructor, and down here I have a 2-3 pair in the 1 constructor. So every time you kind of go down one level, you end up storing pairs of the elements you had before. So the topmost level stores the actual integers, then you have pairs of ints, pairs of ints. And also if you like push something in, you'll push kind of pairs down. And to make this kind of reasoning work, we have to kind of specify what the thunks look like. And for this, there'll be an invariant. So I'll first take the size from a digit, and then I'll say, if I create a deep node, I have this smart constructor deep, which says that your thunk in the middle has at least as many credits as 2 minus the size of the front plus the size of the rear. So if we look at this push thunk, we can see that the node above it has a 1 element in the front. So the amount of credits I need is 2 minus 1, and so I have 1 credit up there. And let's look at a way I would push into a queue like this. So this is the push function, and I'll walk you through it in an example, so you don't have to read all of it right now. So if I push something into an empty queue, I'll just create a new empty thunk in the middle, and I'll put it into the front queue immediately, or into the front digit. Then if I push another one in, so then I'll just add it to the rear digit, and I'll also put 1 credit onto empty, but that doesn't matter because empty is not a thunk. And now I'll actually have to do some work, because because I can no longer put something into the rear digit, like there's already 1 element in, so I'll just push the element 2, 3 that I want to insert, I push down into the middle thunk. And so there's a thunk being created here. And I'll also add 1 credit, because the size of the front is 1, so I need to add 1 credit to the new thunk I've created. All right, so let's say I keep pushing things in. So then the 0 turns into another 1 digit. And I actually put another credit on here, so I now have 2 credits on the middle thunk. And then I'll actually have to force this, which means I'll now take the credits I've accumulated on this thunk to push the tuple 2, 3 into the empty queue in the middle. And of course, there I have to spend 1 tick at the start, so that tick will come out of the credits I have accumulated on the thunk. And then I create a new thunk here, which again, for this queue that has the tuple 2, 3 in it. And I'll again put 1 credit on it. And so this style of reasoning about these lazy data structures is something I call this credit passing style. So the idea is you have these credits on there, and you always move credits onto a thunk, and then once you actually evaluate the thunk, you use the credits on the thunk to pay for it. So there's 3 operations here that matter. There's tick, that costs you 1 credit from the thunk that you're currently evaluating. Credit width, which transfers 1 credit. And force, which is always free, but it can get stuck if there's not enough credits to pay for it. And this model of reasoning about lazy data structures is something that is, I think, very much inspired by Okasaki's work. So Okasaki has this notion of debit passing style, which was also formalized by Danielson, I think in Popple 2008, and very recently by François Patier, Gounod, Jordan, and Mevel, also at Popple. Right, so there's this, so now that you understand what amortized complexity is and how to reason about it, let's think about what we can do to actually check that our reasoning is correct. And so, of course, these papers have used proof assistance to verify that it's correct. But this being the Haskell workshop, I want to use Haskell, and for this I'll use QuickCheck to test probabilistically whether our reasoning is correct. And so the first thing I need to do is I need to specify the cost bound, so I need to specify how many credits it should even have. And for this, I'll have this class called a data structure. You can create a data structure, potentially using some laziness. You can also perform an operation on it. So if you have a size for the data structure, an instance, TM, and an operation, you need to specify what happens once you perform this operation on the data structure. And given a size and operation, you can specify what the cost should be. So how many credits do you need to actually perform this? So let's look at this for this example, right? So what the operations I have are pushing and popping. So I can push one element, and I'll create a QuickCheck instance that creates a bit more push operations than pops, so that like my queues kind of grow over time. And so my implementation will be to create. I just create an empty queue. To perform a push, I update the size by 1, so I add 1 to the size, and I perform the push on the queue. And to do a pop, well, I try to pop, and if there's nothing in there, I say like, oh, the size is 0 now, and I return an empty queue. And otherwise, I see the size is decreased by 1, and I return the results of the pop. And then the cost bound I have is that both push and pop should cost 2 credits each. And with all of this set up, we can now just run QuickCheck on it. So my library kind of takes this data structure implementation I've just given you and kind of generates some QuickCheck tests on it. And if we actually run it, we see that, OK, we've passed all the tests. And that's very good, right? That's what we want. But sometimes, of course, you get your reasoning wrong. And one of the nice things about QuickCheck is that it can give you a counterexample. But actually, in this case, the counterexample is not that useful, because we can look at the top bit of the queue. We can see there's a deep constructor. But then there's this thunk in the middle, and it's kind of hard to look into the thunk. So there's not really a lot that QuickCheck can do. And the problem is really in the monad lazy type class I've just introduced, because the delay constructor takes an MA, so a monadic computation in Haskell, which is not really something we can print, because I can't print like an arbitrary Haskell expression. So we need to find some way to defunctionalize this notion of laziness. And this is where, if you've seen my talk on Monday, like this idea of defunctionalizing laziness comes in. And the idea is that I'll just add like a little bit of indirection here. So instead of delaying a computation MA, I specify a type T, TA, that I'll delay instead. And the idea is that TA can be embedded into the monad MA. But I can specify what T is. In particular, I can use a data constructor for this. And then I've just added this little bit of indirection. So I delay TA, and then in the forcing function, I say, now you have to actually turn the TA into an MA that you can run. So what is an example for this T? So the idea is I create a data constructor for the computation I wanted to run. And so I have to use a GIDT for this. But then I can say I have like I push, which is a kind of a delayed push that I want to have. And the way I implement it is by saying, well, the push is just like corresponds to the push computation that I wanted to do. And then in my code, instead of like delaying the actual computation, push x, y into m, I instead just add this constructor. And so I've added like a little bit of indirection here, but the effect of doing that is that I now have a constructor in my thunks, and I can print a constructor, whereas I could not print the computation beforehand. And with this, I can actually now get some counterexamples. So for this, I modified my implementation to be slightly wrong. So let's say I run QuickCheck now on this wrong implementation. Well, I first push one element in, and I can see, OK, I now have the deep queue with 1 on the front digit. And I can already see that the thunk can now be printed, and I can see the thunk actually is an empty. And then I keep pushing more things in. And at this point, I've actually now created this push computation, which again I can print on the console. And I also have like the small, so on the arrow, you can see there that I have the small 1, and that is the amount of credits that this thunk has. So if I want to reason about if every thunk has enough credits, I can just look at this terminal and see whether that is true. And so I keep pushing in, and so at some point I even have 2 thunks. So in the big queue I have this thunk number 4, which corresponds to this push computation, which again has this thunk that corresponds to the inner empty. And at some point, I'll do the pop, and this is actually where I made the mistake in my implementation. And we'll just say like, oh, sorry, I'm out of credits. I tried to evaluate thunk number 4, but I couldn't because there's not enough credits on this thunk. And then you can kind of start thinking about like, well, what did I do wrong probably? But you'll have like an example in front of you and can just draw it on a piece of paper and kind of think about like, yeah, what you're missing. So the results of this are, you can use this credit monad style to analyze almost all data structures of Okasaki's book. So I went through Okasaki's book, I implement all of these things and all of these data structures in my Haskell DSL. And the credit monad was good enough for almost all of them. There's 3 exceptions. One is the banker's queue, which is actually one of the first examples Okasaki's presents, but is, I think, quite tricky to analyze. And for this, I have a more advanced principle that I call credit inheritance and that you can find in the full paper. There is catenable lists, which are another data structure that Okasaki presents, using another complicated analysis, and that is, I think, something that I'll have to look at in future work. And also there's an implementation of the implicit catenable DAC. I think that's the last data structure in the book. And so there's one case in the concatenation of these where my analysis fails, and I have to investigate why that is. I also looked at finger trees, and so I checked that all of the operations work. And I noticed that the measurement is actually not so easy. So you can't implement measurement just with a smart constructor, but you have to do something smarter. I had one solution. I then emailed Ross Patterson, who had a better solution, and I have all of this written down in the full paper. So thank you.
Questions? Yes.
So in the paper, you give a link to the credit monad package that's
Yes.
on GitHub, presumably.
On Hackage, yes.
On Hackage.
Yes.
So, but this paper doesn't have this kind of artifacts badge on it. So my question is, how much can someone with just the credit monad package on Hackage duplicate the work that you have done here? Because it's like all of the whatever, it's like the testing harness and whatever is probably not, presumably not in the Hackage, right?
No, it is. It is. So I put all the implementations of Okasaki's data structures in the package as well. Mm-hmm. So you have, I think it's called control monad credit, which is the credit monad, and then it's, I think it's test something, maybe test credit.
So pretty comprehensive.
Yeah, so there's all the implementations on there, and one of the reviewers of this paper also mentioned that they found it easy to use and that they tried it out and like that they could use it for like a simple example.
So you could pretty much reproduce all the results.
I think so. I think it is. Yeah, and if you have trouble using this, please email me. So I'm very happy to help.
Hi. Yeah, thanks. That was really interesting. I've not seen this implicit queue data structure before, but I'm wondering, does the same, can you apply this reasoning to these simple queues that you started the presentation with? And if not, is there any reason why you didn't present it with this? Is it more interesting using these implicit queues or something like that?
Yeah, so unfortunately, using laziness is, it's a bit tricky. So in particular, the problem is you need to put the thunks in quite early, because you can only start accumulating credit on a thunk once the thunk exists, right? And so even if you start with something like the simple queue, you actually have to do a lot of adjustments to put the thunk in and make sure that it all works correctly. Yeah, so right.
So does this mean that sort of you couldn't use this kind of framework for analyzing the complexity of this, or do you just mean that you would have to, it just wouldn't look so nice?
So this simple queue is just doesn't work in a persistent setting, right? Like you need to change the data structure to add laziness in order for the amortized analysis to be possible at all. And like Okasaki presents a bunch of versions of this, and I've analyzed them, but they are still a lot more complicated than this simple example.
Cool, thank you.
Yeah.
Sorry, is there one? No, it's fine.
Hey, cool work. I'm curious, when you went and implemented every single data structure from the Okasaki book, did you write any bugs that you found using credit analysis?
Yes, yes. Yes, absolutely. So I mean, the reason this interface looks so nice is that I had to rely on it a lot. So yeah. Oh, sorry. So I mean, like these were bugs I introduced, right? I should say, right? Yeah, but like, yes, yeah, yes.
Okay, so when you're done testing with your DSL thing, right? So I guess you need to translate your testing implementation of a data structure to a production implementation, right? So is that translation like completely mechanical that can be automated, or?
So we're not automating it, but yeah, I think it is relatively straightforward. So I mean, the main way this differs from like a production implementation is that, of course, this is all in a monad where all of the laziness is kind of in this explicit form. So you have to get rid of that, but yeah.
Okay.
I think it's not too hard to do that.
The other question is, so the examples you show, like push and pop, these are basically like unary operations. So do binary operations like the union operation on the map, or like arbitrary or arity operation, do they work the same way, or?
Yeah, I think so it is a lot harder to test them well for two reasons. One is that I think it's not a good idea to write a QuickCheck generator for like one of your data structures, because then you have to think very hard about like what the invariance of your data structure is, and like I think that is a lot harder than writing a generator for an operation, the way I've done here. So what I do to benchmark something like the merge of two heaps, for example, is that I actually build two of them using these random operations, and then periodically I generate like a merge operation that merges them together, which is a bit more indirect, but I think works very well within this testing framework.
Okay, thanks.
So for the previous question about extracting a real program out of this, do you have any, like, have you tried to see if GHC is able to get rid of most of the monad noise if you just interpret everything into the identity monad and things into themselves and so on and so forth?
I have not, but yeah, that would be an interesting thing to try. Yeah, I agree.